Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for double integrals over general regions and properties of double integrals. So first we're going to talk a little bit about theoretically how would you compute double integrals over general regions. So it doesn't matter how the shape of your region is, you can always do this. We already know how to compute double integrals over rectangles by using Riemann sums in particular. So the thing that we're going to do is now, suppose that we want to compute this volume under the surface over the region. I'm just assuming that the function is positive. It doesn't change too much if for some reason go underneath the xy plane. So the idea is the following. Given that this region, you can use rectangles to compute the double integral by doing this. Once you have this region, enclose the region in a rectangle. So once we have the rectangle that encloses the region, we're going to define a new function. The function is going to be as follows. F of x, y, capital F of x, y is going to be the same as the function if the point is in the region and 0 if the point is not. So the graph of the function is going to look something like this. So notice that given the graph of the function, we have that the double integral is going to be equal to, over the region D, is going to be the same as the double integral of the new function capital F over the region R. So why this is useful is because then we can just compute this as a double integral over a rectangle. The only problem is that f of xy may not be continuous. This means that we can apply Fubini's theorem, so the only way that we can compute this double integral over this rectangle is using Riemann sums. The other reason why this is important, or this is going to be useful, is because we are going to be able to prove well, we are not going to do it in this video or in this class, but you can prove the properties of double integrals by just proving the properties of double integrals over rectangles. So here are the properties that I'm talking about. The double integral of the sum is the sum of the integrals. If you have a constant multiplying the function, you can move the constant out. If you have that a function is bigger than another function, then its double integral is going to be bigger. The next one tells you something that actually is very useful, is that every time that you have a region, you can split it into two regions that they don't overlap except in the boundaries. Then the double integral of the big region is just the sum of the double integrals of the two regions that you split the big region into. So in this case, D is split in D1 and D2, and you can just compute each individual double integral over the regions D1 and D2. One other one that is important is that you can compute the area of a region by just taking double integration, and the idea is pretty simple. Suppose that you want to compute the area of the region D. The thing that you do is you just take the constant function 1, and remember the volume is the double integral of the function over the region, but in this case the function is 1, so you have that the double integral is going to give you this volume, but at the same time the volume can be computed in this particular case by the area of the base times the height. The height is 1 and the area of the base is D, so you have that the area of D is equal to the volume. So in other words, you can compute the area of a closed bounded plane region D as the double integral of the function 1dA. Notice that in this case we're taking the function to be the function constant 1. Let me give you an example. So if you want to use double integrals to find the area enclosed by the parabolas x equal to x squared minus 1 and y equal to 1 minus x squared, the thing that you do is the following. We have these two parabolas here. I already have drawn them, and the only thing that you have to do is to take the double integral over D of the function 1dA. So let me express the region D, and notice that since we are trying to evaluate the double integral over D and D is not a rectangle, it's convenient to check if it is either a type 1 or a type 2 region. So in this case, D is of type 1. First, we have to find the points of intersection of the parabolas. In this case, the points are minus 1, 0 and 1, 0. So the region D, as I said, is described like this. The y moves between these two parabolas. The parabola on the top, the parabola on the bottom is the red parabola, x squared minus 1, and the parabola on the top is the green parabola, so it's y equal to 1 minus x squared, that is over here. And then the thing that we're going to do is that the x moves between minus 1, that is the x coordinate of this intersection point, and 1, that is the x coordinate of the other intersection point. So the thing that we have is the double integral of 1 dA is going to be equal to this by the generalization of Fubini's theorem. We integrate first with respect to y, so you obtain a y here, and we obtain this integral over here. This integral is more or less the way that we will have compute the integral using only single variable calculus. So notice that we're doing exactly the same thing. Then we integrate that and we obtain that the area is 8/3. One of the things that you have to know, that I would like you to notice is, first of all, this is not something new. You could compute these these areas by not using double integrals. And the other thing is you can do this in different steps. You can actually compute only this area over here and multiply it by 4 by one of the properties of double integrals. Anyway, but one of my points here is kind of show you how we can use this, and if we can extend the integrals, the regions in which we can take double integrals, we can simplify our way to compute areas. So in order to finish, let me just give you the formula for the average value of a function of two variables. Since a function, a double integral, is actually a Riemann sum, in other words, a sum of a lot of values of the function times the area of each one of them. If you divide by the area of the total region, the thing that you are going to obtain is a formula for the average function, the average value of the function, and it's given by this formula. And with this, we finish this tutorial. Thank you very much.